All right. Welcome to Recitation 7 for fluids. You all know the drill at this point. This is Recitation 9. Did I say Recitation 7? Recitation 9, whatever. All right. So it's all about pipe flows and things like that, turbulent and laminar pipe flows. Even though for the case of the problems we're going to be doing in these, I'm not even going to talk about if it's turbulent or laminar or not. It doesn't matter. You'll see the math we do. It'll not depend on if it's turbulent or laminar or not. Your next homework will deal with all that stuff, so you'll get drilled on that at some point. But for this first one's pretty brutal. Like I was saying, this will be probably considerably more difficult than what you will have to do on an exam. It's very lengthy. There'll be a little twist at the end that you'll see that you'll be like, whoa, that's tough. So don't worry about it. But so for problem one, we've got water at 15 degrees Celsius, which again doesn't really matter in this case, but it's for the properties of the water itself that is why you care about the temperature. The water is at 15 degrees and it's being pumped from reservoir A to the large tank B. Power output of the pump is 3.7 kilowatts, determine the volumetric flow into the tank when H equals 8 meters. Commercial steel pipe has a total length of 30 meters and a diameter of 75 milliliters. Include minor losses for the elbow and sudden expansion into the tank. All right. So right away we're going to define some points right here. Call this point A, all right? And so we're going to say pressure at A equals velocity at A equals 0, right? We're just going to define those as 0. This is a big tank, or so it's a lake, it's a big reservoir. Same thing up here. And say PV equals VB equals 0, right? Okay, cool. And so now let's just write down all the constants and stuff we know. I'm not even going to write the temperature. Like I said, it doesn't matter. It'll just affect our density and viscosity values. So we're going to say rho, we're just going to call it 998, call it that. All right, let's see what else. What all do we know? We know height H equals 8 meters. All right, let's see what else we know. We know W dot is the power, 3,700 watts. I'll just convert it. We know the length of the pipe. Total length is 30 meters. We know the diameter, 0.7075 meters. And then also from the temperature we can get the dynamic or the kinematic viscosity, nu. And if you go and look it up, go find somewhere to look it up. 1.15 times 10 to the negative 6. And that is meters squared per second. I believe you've seen it there. Okay, and then so it says include the minor losses for the elbow and sudden expansion in the tank. Okay, so unlike an exam or on a homework or something, you'd be given a table of minor loss coefficients where you'd have like, so you see you've got 90-degree elbow here, and then you'd have a table that'd be like, oh, if it's a 45-degree bend, it's this value. If it's if it's a valve, it's this. If it's an expansion, it's this. And so they don't give that here, so I'll just write it here. So I'll say KL, that's how you usually know it. KL, I'll say 90 degree equals 0.9. And then KL EXP for expansion, it's just 1. And those will come in a second. But should be everything we need to start off. Oh, also, another part of this whole thing is we need to know the epsilon value for the surface roughness of this pipe in here. And again, they don't give it to you, but think about it physically, like you can't make a perfectly smooth pipe. There's gonna be like friction inside the pipe. That's why we're doing this whole thing. So inside of the pipe, you're gonna have little bumps and imperfections. And so you denote that as epsilon. And it's just it's basically the height of the little tiny grooves in the pipe as it's being manufactured. And they have that as 0.045. And again, that's in whatever length scale is for the province. So in this case, it's meters. And actually, this is pretty big for an epsilon value. It'll usually be at least like 0.00 something. This is actually pretty big for what it's worth. You'll see that come up a lot, but All right, we should be ready to roll. So, first off, we want to find the volumetric flow rate, okay? And so first, basically step 0 for a problem like this is try and find your Reynolds number, right? Try and go and find some Reynolds number. So let's do that. So we know Reynolds number equals some velocity times your diameter over your kinematic viscosity. This is because, kinematic viscosity is just, mu over rho. So you can write it like that. Rho VD over mu is also a valid way of writing it, whatever. But if you notice, we don't know any sort of velocity value, which, spoiler alert, is going to make this problem really, really hard. If you can't find a velocity value like straight away within the first couple steps of your problem, it's going to be a tricky one. So for now, we're going to solve everything in terms of this random velocity value that we're going to go and find later. So we know our kinematic viscosity, and we know our pipe diameter. So just plug those in. I'll rewrite it as RE equals 6.52 times 10 to the 4 times velocity. Times whatever the velocity value is. And remember, that's a dimensionless number that has no units to it. That's the whole point of a Reynolds number. Okay, so we've got that. And can't really do anything with that, but finding a Reynolds number is always a good starting point. Like if we knew the velocity, we'd be able to tell if it's turbulent or laminar or not. We don't know, so whatever. But like I said, it doesn't matter in this case. Okay. So moving on, it wants us to find the losses in the pipe and all that. So let's try and find the major losses first. And you guys have talked about like major and minor losses and stuff, right? No? Oh, dude, that sucks. Okay. So think about it like this, okay? In a pipe, and we're assuming that there's friction in this case, right? We're assuming there's some friction present. It's not inviscid anymore. So as you're pumping water through a pipe, obviously you're not going to be just pumping it scot-free, right? You're going to have some sort of friction loss in the pipe due to the interaction between the pipe walls and whatever liquid. Because you remember that no slip condition and the shear stress stuff you did? That's really what's going on inside a pipe. Like that first week when you did the tau equals mu times du dy, the shear stress, that is a friction force, a shear force that's pulling on the water. So obviously you're going to be losing a little bit of energy there. And so there's two types of losses in pipes. There's the major losses, which is like directly from the friction from the pipe. And then there's minor losses, which like, in this case, when you go around a 90-degree bend, you lose a little bit of energy. It's not totally, you can't just conserve all that energy. So usually the total friction losses in the pipe are going to be bigger. That's why it's called the major losses. And then the little bends and stuff and expansions where you lose just a little bit of energy, that'll be your minor losses. They'll be a little smaller. But it's not totally universal though. If you have a really short pipe with a lot of bends in it, obviously your minor losses could be a little bigger than your major losses, but it's just terminology. So we'll say HF. You usually call the losses HF, and that's equal to HF major plus HF minor. Wow. Profound statement right there. But so for the two components, for the major component, it's called like the Darcy-Weibach equation or something like that. Whatever you want to call it, doesn't matter. But this is just an equation that you'll be given. So it's HF major. It's F times L over D times V squared over 2G. Okay, and that's, I'm sure your professor will probably go and do some big derivation of it. Whatever. This is what it'll spit out. Where F is some friction factor, which we'll find here in a second, and you'll see it can be either really easy or really difficult, like we'll see in a sec, and then just length over diameter and velocity squared over 2 times gravity. So that's your major losses. And so you can see if you have a really short pipe, this whole thing would be a lot smaller. And also this friction factor is usually like 0.02-ish in that ballpark, so also really small. So the losses themselves aren't very big, but whatever. So first, let's just plug in what we know. In this case, this will be solved in terms of the friction factor we don't know and the velocity squared we don't know. But everything else we know, so let's just plug it in. So So HF major equals FV squared times 20.3874. And important to note, the losses and stuff in the scope of this form, it'll be in whatever length scale unit you're talking about. So in this case, it's meters, okay? And the way I think about this physically, and I don't know if it's necessarily the right way to think about it physically, but when I read that number, I think, okay, due to the major friction losses in this pipe, I'm losing like 20 meters of available like pumping distance. I don't know if that's the right way to think about it. I don't know if that's actually what's happening, but that's just how I quantify what's being lost, whatever. Okay, so we've got that part. Now for the minor losses are usually a lot easier to find. And it's also just an equation you'll be given. I don't know the name of this equation, just the minor loss equation. So it's the sum of your loss coefficients KL times V squared over 2V. Right. And again, this is in meters or whatever. And so literally just, you've got your two loss coefficients over here. Normally, like I said, you have a big table full of them. But just plug them in and then add them together. So in this case, since we're gonna have the same, and this V squared, this is the velocity inside the pipe, okay? So like at VA and VB, it's 0, but obviously there's some velocity inside the pipe. So, and we're gonna assume that's constant. We're not gonna be fiddling with the velocity inside there. So velocity is the same, gravity is obviously the same. So inside of this sum, we're just gonna, like when I would go to plug it in, I would just call this 1.9. I'd just add the coefficients together and then just do normal math from there. So adding everything up, the HF minor equals 0.09684 V squared. Right. And you can just see like visually, of course, like this number would be quite a bit smaller than this one. Even with that really small friction coefficient, it would still be a pretty small number. But okay, so we've got that stuff. Say, all right, now what? Well, let's add them together for HF total. Yeah, adding them together, and you could factor out a V squared. I'm not going to. I'm just going to write FV squared plus blah 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 times 20 point. Factor it however you want. Doesn't matter. Yeah. Okay, so anyway, and also it's important to note, usually in other applications I've been like, lop off your decimals wherever you want, like you just round smartly. In this case, try and carry as many decimals as you can throughout the problem, because you're gonna be dealing with really small numbers throughout this whole thing, like you'll see here in a little bit. So I say 4 or 5 decimals for something like this, that's usually fine. You can carry around as many as you want, doesn't matter to me. But yeah, just don't lop it off at don't call this like 20.4. Don't call this 0.1. Like that would be, you get a significant error at the end of the day. Okay, so now we've got technically speaking, this is our major loss term. We just don't know the values in it yet. So what we're gonna do, we're going to now take this Bernoulli's-ish equation. You might hear it called Bernoulli's equation for pipe flows. It's not really, it's like a derivation on the energy equation. Technically speaking, for Bernoulli's equation, you need it to be inviscid, and you can't have any work being done or anything like that. So it's not really a Bernoulli's equation, whatever. But it's that vibe, okay? So you'll see what I mean in a second. So it's PA over rho G plus alpha A V squared A over 2G plus ZA plus HP equals so yeah, I mean, you can see like it's very Bernoulli's vibe, you know. But this ZA is, you know, the heights, and the ZBs are the heights. The HP is like the work of the pump work, which is that, we know the pump work over there. And then HT is if you have a turbine in here, it's the work from the turbine being extracted by a turbine. Obviously there's no turbine in here, so we're not gonna have anything there. And then HF is the losses. So let's go and clean this up. Like we said, pressures and velocities are 0. So let's get rid of those. Oh yeah, and the alpha A and the alpha B, those are just coefficients that you assign to the velocities, and they depend on if it's turbulent or laminar or not. I believe if it's laminar, it's 2. If it's turbulent, it's 1. So not very difficult math there, but you can see I'm not even talking about it much because velocities in this problem doesn't matter at 0. You would also call ZA 0, and there's no turbine. So we get HP equals ZB plus HF, right? And so start leveraging that equation. So we know that W dot, or I guess I misspoke there earlier, whatever. But we've got W dot, the work from this pump, is equal to rho G Q times H pump. Guess I'll call it H. Okay, cool. So go rearrange this, because we ultimately want to solve for like this H pump, because that'll get us all the other stuff we need to know. So let's go H pump equals W dot over rho G Q. And remember, Q is equals V times A. Right. So now go rearrange this whole thing. So we've got W dot over rho G Q, or I'll say rho G V A, right? Or rho G V D squared over 4 times pi, if you prefer, or whatever, equals ZB, it's the height, so that's 8, plus our HF, which is FV squared times 20, blah, 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 blah. Plus 0.09 since it equals. All right, okay, and so now, obviously, if we plug in all those other numbers, we can get the H pump sitting there, you know. And finally, once you plug in everything, I'm not gonna show all the algebra for it because it takes a while, but you know, plug in 3700 here, plug in 998, 9.81. We're still gonna have some velocity term floating around, plug in your diameter, plug in pi. We're gonna set this whole equation equal to 0, and then get all the like velocity and stuff and F's on one side. So this will work out to being 0 equals 20.3874 F. Plus 0. Times V cubed plus 8V minus 85.4413. Okay, so now you're sitting there, all right, we still don't know our F and we still don't know our V. We kind of went in circles there. But what we can do now, we can use what's called the Colebrook equation to try and solve for the F value. All right, and I really like the Colebrook equation. There's 2 ways to get your F value, your friction factor value. One of them is to use a Moody chart, which is very thermo-y, looks like a thermo kind of chart, and I'm not a big thermo guy. I just like using an equation and plugging it in. But anyway, the Colebrook equation is really cool too. Have you guys seen it? It's an iterative equation. We talked about the Colebrook equation at all. That was pretty sweet. So I'll write it right here. So we got Colebrook. It's 1 over root F equals -2 log. And this is log base 10, not like natural log. On your calculator, use the LOG button, not LN. have 2 log epsilon over d over 3.7 plus 2.51 over RE times root f, all right? And it's kind of an equation soup E looking thing, but it's really not bad. So how you go about solving this, right? What you do, okay? You ignore this left side for a second, and then you pick some random f value, literally pluck a number out of thin air, okay? And you can pick whatever the hell you want. Use that value, plug that in for f, and this would be like assume you know a Reynolds number, okay? Solve this right-hand side for that random f value you chose, and then let's say this works out to be like 100 or whatever. Use that and then solve for this f over here, and this becomes your new f value. And so you wipe everything clean, use that new f value, plug it in over there, repeat the whole thing, solve for another new f, plug it in, repeat, until those 2 f values stop changing, until they converge on a solution. All right. And if you're smart, that should only take like 3 or 4 steps. I will say pick an f, right? Pick an f value. I will say usually, underline, usually around 0.02. All right, so usually around 0.02. If you're really in a jam on a test, putting an f value of 0.02 will usually get you pretty close to the answer. Obviously, like if you don't show the equation, we won't give you the points for it, but you'll get where you need to go for the most part. So, but you can see, okay, so in order to be able to pick a smart f value and iterate and get the actual f value, you need to know your Reynolds number. In order to know your Reynolds number, you need to know a velocity. So in this case, you're iterating over like 2 different numbers, and so it would be really hard because you'd have to go, essentially what you do, the way I would do this, I would like pick a random velocity value, right? And from that velocity value, it would get me some random Reynolds number, then I'd use that Reynolds number, and then I'd pick a random f value, and then start iterating. And then I get a new f value, and so I'd have to get a different velocity value, blah, blah, blah. Like you can see, this would suck to do on an exam. You'd be here you could say you're gonna do this all day if you wanted to. So, what you do in this case is you would write a MATLAB script that just iterates over a bunch of stuff for you. And so, that's actually what I was gonna say. I'll say write code to iterate. All right. And then after you do that, after it converges and everything, you end up getting an f value of 0.018739. Like I said, pretty close to 0.02. And this is like, and for this really, like keep some decimal places on this. This is kind of important. But, pretty close to 0.02, whatever. And so now use this, go solve for your v. You get v equals 4.652. And then now we know our velocity, so now we can plug in and find our volumetric flow rate. Okay. And so using that, we get Q equals VA. Q equals 0.0205 cubic meters per second, right? You can see how on an exam that would be pretty brutal, having to sit there and iterate for hours and hours over like 2 different values, having to find one to go and guess another one and repeat the whole process over again. That would take a while. On an exam, if you are going to have to iterate, it'll be like you'll know like a Reynolds number, you'll know a velocity, it'll be a lot smoother. But yeah, if you pick 0.02 as your starting point, you can usually get this whole thing to converge in like 4 steps tops. If it's like a really bad situation, it's not gonna be that bad. And it's pretty, once you start getting used to the equation, you can really type this stuff in fast. It's actually kind of fun. But, Yeah, this is literally worst case scenario. If you see something where you don't have a velocity straight up, and therefore you can't get a Reynolds number straight up, you're gonna have a rough time. But that's why this is a really good resource to have actually once we post this. This might come in handy later. But any questions there? This is probably all fairly new stuff. Just follow these equations. There's not a whole lot of like calculus that'll need to be done in this section. Everything's pretty pluggy and chuggy at this point. Just gotta focus on what you're actually trying to find. You know, a lot of times I'll be doing some of these, and I'll just start finding all sorts of different numbers and all sorts of different velocities and stuff, and I'm like, what am I actually trying to solve for? And so just keep that in mind when you're doing these. You're gonna get a bunch of crazy numbers laying around. So, but in general, these problems aren't too difficult. There's like 4 different types of them you can see, and this is, like I said, the worst one. Okay, any questions before we move on to question 2? It's considerably quicker than this one. It's a lot easier. So don't worry about that. Cool. Anybody need to take a picture of this before I erase that? Good, okay. Yeah. We have 15 seconds. Got places to be. Let's go. Kidding, I don't care. Cool, all right. Here we go. Question 2 is a similar sort of vibe, but we can get a velocity and a Reynolds number straight out of the gate, so it's a lot better. I would say this is actually kind of like my second favorite unit to teach in this. I mean, you just plug in the numbers and I always like the Colbert equation anyway. It just feels like magic to me. You literally pick a random number and it spits out the right answer every time. That's why I don't like using the Moody chart, because when you use a chart, you can only get so accurate, you know? I mean, technically speaking, the Colbert equation is an approximation as well. Like, there's no real way to get like a legit, mathematically perfect answer from these, but the Moody chart sucks because it's an even worse approximation because you're just using your eyes, so whatever. Yeah, you can see here's all the stuff, blah, blah, blah. I lopped it off at 6.52, but you didn't really need that number anyway, so who cares? Let's see, oh, here we go, okay. So, let's see if I can zoom in a little more. Okay, so problem 2 is this bad boy right here. All right, so we've got oil of a specific gravity of 0.88, and this is supposed to be new kinematic viscosity. You can tell by the units it's in. Flows at 400 gallons per minute. Oh yeah, and this is all like imperial. It sucks. We're doing for everything to imperial from the jump, so keep those values in mind as we're going through this. But, all right, flows at 400 gallons a minute through a 6-inch asphalted cast iron pipe. The pipe is half a mile long and slopes upward at 8 degrees in the flow direction. Computing the head loss in feet and pressure change, use epsilon equals point. See what I'm saying? This is like a more realistic epsilon value, like tiny. Anyway, okay, so we're going to be computing the head loss in feet and the pressure change. And for this one, it doesn't say it, but we're going to be ignoring any minor losses. Obviously, we're just, it's implying that there's like no changes, like no bends or anything like that. So there's no real minor losses to account for anyway. So again, let's write down what we know. So we know specific gravity is 0.88. So we're going to have rho g, rho equals SG, so 0.88 times the density of water, which is 1.94 for, call 1.94 in imperial. This will get you 1.7072 or something like that. Yeah, 1.7072 slugs per foot. All right, cool. And then we know kinetic viscosity. I'm just gonna write it in the converted value to like square feet per second. It's 4.303 times 10 to the negative 4. Square feet per second. Let's see what else we know. All right, we know Q is 400 gallons per minute. So converting that to cubic feet per second. Q is 0.891. Cool. And then let's see what we know. Diameter is 0.5. We have length equals 2640 feet. Epsilon, or roughness, is 0.0004 feet. Okay. Anything else you know? Oh, theta. Theta equals 8 degrees, which will come in handy later when we're finding the delta Z thing. Should be good to go. All right, so starting off, we know, like I said, we always want to try and find a Reynolds number first, just because. And so to do that, we need to find a velocity value. And in this case, it's nice. We can get a velocity value because we know our volumetric flow rate. So I'll say Q equals VA. And so V equals Q over A. So plug everything in. You know the diameter, and you know the volumetric flow rate. So V equals 4.538 feet per second, right? Okay, and from there, let's get a Reynolds number so we can calculate our F value. So it's UD over nu. So plug everything in. We now know our velocity, we know our diameter again, and then we've got kinematic viscosity. So again, Reynolds number equal to 5274. Did they talk about the turbulent and laminar boundary for pipe flows? Did you talk about that yet? Yeah, what is it? It was like 2300, isn't it? I always forget what it is for pipes. But yeah, so this is turbulent, of course. And in this case, it doesn't really matter anyway, but whatever, it's turbulent. If it was less than 20, oh, if you ever got a number right around 2300, where it's right in that boundary, you probably did something wrong, because once you get, so we have equations for laminar, we have equations for turbulent. We don't really have anything for the transition zone. So in the scope of this class, you're probably not to be asked to do that, just for what it's worth. If you do get like a number that's right in that boundary, it will probably mean, yeah, either A, you did something wrong, or B, it just won't matter, like the Reynolds number just won't come into play in the problem. But that's an aside, whatever. But anyway, all right, so it's turbulent, okay? So now, straight up, we want to calculate the head loss in feet and all that. So we want to find our F value to get our, F L over D, and all that stuff. So let's go find F. All right, and let's go 1 over F equals -2 log plus. Right, like I said, pick an F value. It theoretically can be whatever we want, but pick 0.02, whatever. Iterate, and so end up getting an F value of like 0.03 in this case, I believe. Yeah, 0.0377. It was actually pretty high, but I mean still pretty close to 0.02. That's a good start point. So from here now, we'll say find HF, and I guess I'll move it up like to here. And in this case, HF is just the major losses. Like I said, there's no minor losses in here. So we'll say HF equals F times L over D times V squared over 2G. And again, found our velocity, found our friction. We're good. Let's plug everything in. HF equals 63.678 feet. So boom, there's first part of the question done. Cool. So now we want to find the pressure change, right? And for the pressure change, you use that Bernoulli's-ish kind of equation where you have all sorts of pressure terms, right? And so we're going to go. All right, so we're gonna assume this is coming from a bid reservoir and going into a bid reservoir. It doesn't explicitly state it, but you know, like 90% of things in this class, you just have to assume stuff. Write down what you assume, it'll be fine. So we'll say point A, somewhere down low with, you know, stagnant conditions, P is 0, V is 0, and then point B is somewhere really high up, same 0, 0 stuff, but now there's a height change. So we're gonna say PA over rho G plus alpha A plus So like I said, we're assuming it's coming from reservoirs, so we're gonna cross out a bunch of stuff. Well, I guess, okay, so we can't call the pressure 0 necessarily. That's what we're solving for. We're solving for the change in pressure. We can definitely call the velocity 0. Then ZA, we're gonna call it 0. We're gonna call it HP, we're gonna call it 0. There's no pump. And then for all of us, we're gonna say that's 0, and then loss is obviously 0. So rearranging this, what I'm gonna do, I'm going to multiply the rho G's over, okay, so we can get everything just in terms of pressures. And so this form of this equation is the head loss form of it. When you multiply the stuff over, when you multiply the rho G's, distribute the rho G's to everything, and get the pressures of the lone terms, you get it in the pressure loss form. So I'm not gonna show the algebra for it, we're literally just distributing the rho G's to each thing that's left. So you get PA minus PB, so delta P ends up being rho G times ZB plus HF. All right, and so we know HF, we know rho, and we know G, but what's the change in elevation? Well, we know how long the pipe is, and we know the inclination angle. So just delta P equals rho G times this elevation change, the length of the pipe, times sine theta, right? It's just trigonometry, plus HF. We know HF, we know theta, we know L, we know rho, we know G. So go plug in all the numbers. Yeah, you're basically done at this point. We get delta P. Delta P equals 23,698. PSF, pounds per square foot. Cool. So yeah, that one's way quicker. You could find a velocity straight up, and so it makes your life a lot easier. Yeah, like I said, a lot of these problems are just find a number, plug it into an equation, use a different number from that equation, plug it into another equation, and you just keep going. Just gotta find a bunch of numbers, just gotta do a bunch of math. But yeah. Anyway, any questions there? Everybody all good? Everybody cool? Yeah, this is not that high level of a concept. You just plug in a bunch of numbers. Just know when to apply the equations, and really your step one for a lot of these problems should be trying to find a Reynolds number and a velocity value to get that Reynolds number. And then from there you can make a lot of stuff happen pretty quickly. So anyway, yeah, this will be posted later tonight or early tomorrow morning. If we forget, email me. I'll make it happen.